Okay, hello, I'm Curran Edland, and I'm going to be focusing on a little more general of a topic today with solar power, and yeah, so let's get started. Fortunately, that's not the best format, but okay, so why is it important to implement solar on a large scale? Well, I'd say there's a lot of reasons, a lot of environmental reasons, but the main reason is basically just to preserve a stable climate for future generations. We rely on fossil fuels a lot, and if we can implement more solar power, then that means less CO2, smaller carbon footprint, and basically a healthier planet, and so forth. What kind of potential does solar have? It's really unlimited potential. An hour of, or yeah, what is it? I made changes since the last time. Okay, let's see, what am I trying to say? Okay. I want to say an hour of the sun's energy on the planet, of radiation on the planet is greater than the amount of energy it takes to run the world in a year. So really, solar it has unlimited potential, especially in places like Northern Africa, American Southwest. So what has been done? One cool project that I wanted to recommend was, one cool project is NER1. It's a concentrated solar power plant in Morocco. It's currently at 160 megawatts with plans for 3 more similar projects. The final project would be able to create renewable energy through solar panel for 20 hours of the day, which is through the use of like molten salts to store heat energy for running an electric generator later in the day. So kind of a cool thing. That is not newer one. Okay. So there's 2 major forms of solar generation. There's heat, the use of heat energy to power system, or there's the use of sunlight to electricity, as seen in photovoltaics. Newer one, for example, is a concentrated solar power thermal station. It uses thermal energy. For thermal solar, we have 2 forms, active and passive. Active. And the most basic active form of active solar thermal, solar thermal, is like a basic water heater. What you have is you have a plate, usually of copper, heat absorbing material, absorbs heat from the sun, transfers it through by liquid to a heat exchanger in a hot water tank, and that's how you heat the water. A little more complicated application is air conditioning. You can use like a desiccant wheel to evaporate moisture and heat out of the air within a building. Okay, so the next thing would be with concentrated solar panel, these large scale applications where a bunch of mirrors basically just point direct the sun's energy onto a single focal point, heats up water, creates steam, runs an electric generator, like I mentioned before. The second form is through like solar architecture, through this idea of passive solar. So it uses special components like windows, facades, and then like solar architecture is the way a building is oriented or the locations it's in. One example of passive solar is with this figure up here. Say you're in Germany, the low winter sun can provide heat into the house during the winter, but the roof overhang prevents the sunlight from reaching the house in the summer. So you can use that to, it's basically just a different way of looking at how to heat a building. Also with insulation, there's double pane windows with like gas in between the panes. That helps, that decreases heat transfer across out of the building. So the next major form is photovoltaics. So basically, it's due to the principle that a semiconductor, or certain semiconductors, can create electricity when exposed to light. So how a simple solar cell works is you have 2 layers. In most cases it's silicon, but you have a top layer which is has excess electrons, and a bottom layer which has not enough electrons. So you have a negative charge and a positive charge on. So when the sunlight hits the top layer, it bumps electrons from the top layer to the bottom layer, creating a voltage usually around 0.5 volts. 0.5 volts. Then you can create a current, and so on. So that's the basic way that works. So we have, let's see, we have small scale application of PV and large scale application of PV. The only components you really need are a panel, AC/DC converter, and a battery. The cool thing about PV, it's become more attractive in the past years. Like from 2008 to 2013, it increased, I want to say 50%, and a lot of that's because it's gotten a lot cheaper to install, and also smart policies from energy companies and the government have made it a more attractive option through net metering, which is basically the company will buy back the excess electricity that you generate. The large scale application are also there. I think the biggest thing about large scale application that I should mention is that it's actually 60% less expensive to on a per watt basis to create. So that's the biggest advantage with large scale. It takes up a lot of space, but if you implement the right plans and put them, you can put them on degraded land or old landfills or like different situations like that on the side, on tops of buildings. It's there's really no limit to what you can do with large scale solar. Going into solar cell efficiency, first solar cells were created by Bell Laboratories in the 50s. First initial efficiency was like 5%, doubled, and then over the course of like in the 90s, there was a lot of emphasis on it. So we got up to 25%. In like the period 17 years, we went from 15 to 25% efficiency, and now it hovered around 26.3% efficiency for the highest measured efficiency. There's a lot of different materials used for solar panels, but the ones that I'm going to mention right now are monocrystalline solar cells. They operate at the highest efficiency, around 20% on like something that you can purchase, so you can buy one today. But the next would be polycrystalline. It's 13 to 16% efficiency, a little less cheap, or a little cheaper to buy. And then thin film is another one where the efficiencies are lower, 7 to 13%, but it's a lot cheaper than monocrystalline. I'm going to skip over that because I don't have time. But as far as the conclusion goes, I guess what I've learned over the last, semester of researching about solar power and the applications and technologies that come into it is that it's kind of silly that we're not implementing it on a larger scale already, and that each technology has a place. So you're not going to have a active solar thermal water heater in Seattle because you don't get nearly enough sunlight in the year. It wouldn't be a smart move. But in places like Flagstaff, Arizona, where it's very high solar radiation year round, and it's high altitude, so it's low temperature, a solar water heater would be a perfect application. So in conclusion, we have a responsibility as the current generation to preserve the stability of our climate and for future generations, and it's really easy to do. We just need to start, I guess. So thank you.